Hi students, good morning everybody. In this video we are going to see about Kirchoffs rules. Already you have studied about Ohm's law in current electricity chapter. Ohm's law is useful only for simple circuits, but for calculating the current and voltage in complex circuits we have to use Kirchoffs rules. There are two generalized Kirchoffs rules. They are Kirchoffs first rule and second rule. Let us see one by one. Kirchoffs first rule. Kirchoffs first rule can also be called as current rule or junction rule. Kirchoffs first rule states that the algebraic sum of the currents at any junction in a circuit is zero. It is a rule which is based on the statement of law of conservation of electric charges. That is, a charge that enters in a given junction in a circuit must leave the junction. Charges cannot build up or disappear at the junction. So for using Kirchoff's current rule, we have to take a certain sign conventions. Let us see what are the sign conventions. If you consider this diagram, at the point A, which is a junction, there are 5 currents coming and meeting. I1 is the current flowing towards the junction, I2 is the current flowing towards the junction, I3 is flowing away from the junction. You can able to see this arrow mark. I4 is flowing away from the junction and I5 also flowing away the junction. So here when you apply Kirchoff's current rule to this junction, you have to use the sign convention that the current flowing towards the junction is taken positive and the current flowing away from the junction is taken as negative. That is an important sign convention to be followed in Kirchoff's current rule. So applying Kirchoff's current rule to the junction A in this diagram, I can write I1 plus I2 minus I3 minus I4 minus I5 is equal to 0, or I can take I1 plus I2 is equal to I3 plus I4 plus I5. So Kirchoff's current rule states that the algebraic sum of the currents taken at any junction in a circuit is 0. The sign convention to be followed is current flowing towards the junction is positive and the current flowing away from the junction is negative. Kirchoff's second rule. Kirchoff's second rule can also be called as voltage rule or loop rule. Kirchoff's second rule states that in a closed circuit, the algebraic sum of the products of current and resistance of each part of the circuit is equal to the total EMF included in the circuit. This is the statement of Kirchoff's second rule. This rule follows from the law of conservation of energy for an isolated system. What do you mean by law of conservation of energy? According to this rule, the energy supplied by the EMF source in a circuit is equal to the sum of the energy delivered to all the resistors in the circuit. Here, the product of current and resistance is taken as positive when the direction of current is followed. Suppose if the direction of followed by us is not the same as the direction of the current, if it is opposite to the direction of the current, then the product of current and voltage should be taken as negative. For example, if you see this diagram, the current is flowing from A to B. If you follow the loop from A to B, here I have to take as positive. So for this case, as the loop direction and the direction which the current is flowing are same, I can write V is equal to plus IR. In the second diagram, if you take the loop direction from B to A and the current direction and is from A to B, since the loop direction and current direction are opposite, I have to write here V is equal to minus IR. The next one, if you want to write the sign for the EMF, here in the battery the current flows from negative to positive. Here the current flowing inside the battery is same as the current loop taken direction. The loop direction, I can write V is equal to plus E, where E represents the EMF of the cell or battery. If you go from the loop from B to A, as the loop direction and current direction are opposite, I have to write V is equal to minus E. This is very important. Kirchoffs rules can be followed only if the current in the circuit comes to be a constant, or only if a steady current flows through the circuit. Next, Wheatstone's bridge. An important application of Kirchoff's rule is Wheatstone's bridge. Wheatstone's bridge helps us to compare the resistances, and also it is used for determining the unknown resistance in an electrical network. Let us see the diagram and balancing condition for Wheatstone's network or Wheatstone's. This diagram represents the diagram of a Wheatstone's bridge. It consists of 4 resistors P, Q, R and S connected end to end to form a closed loop A, B, C, D. So A, B, C, D is a closed loop or a closed circuit which is formed using 4 resistors P, Q, R and S. And there are 4 junctions A, B, C, D in this network. The junction A and C must be connected across a cell of EMF E, and a galvanometer of resistance G is connected between the 2 junctions B and D. You all know that a galvanometer is a device which is used to indicate whether the current is flowing through the circuit or not. Let us now derive the condition for balancing condition or zero deflection condition for Wheatstone's bridge, applying Kirchoff's first rule and second rule. First step, apply Kirchoff's current rule to junction B. When you apply Kirchoff's current rule to junction B, you know that in this junction B, a current I1 is flowing towards the junction, Ig is flowing away from the junction, and I3 is flowing away from the junction. Before that, let us consider what are the various currents in this circuit. From the battery, a current I is flowing and it is reaching the NDA. At the NDA, it splits up into I1 along P and I2 along R, and the current I1 at the end B splits up into IG along through G and I3 along S, and I4 is the current flowing through the resistance S. Now apply Kirchoff's current rule to junction B and D respectively. When applying Kirchoff's current rule to junction B, we will get I1 minus IG minus I3 is equal to 0, because at the junction B, I1 is flowing towards the junction, IG and I3 are flowing away from the junction. So this equation. Now apply Kirchoff's current rule to junction D, you will get I2 plus Ig minus I4 is equal to 0, because at the junction D, I2 is flowing towards the junction, Ig is also flowing towards the junction, so both are positive, and I4 is flowing away from the junction. So using Kirchoff's current rule, applying them to B and D junction, you will get 2 equations. Now apply Kirchoff's voltage rule to the closed path A, B, D, A. As there is no EMF in this path ABDA, the EMF here is 0. So applying Kirchoff's voltage rule to loop ABDA, we will get I1P plus IGG minus I2R is equal to 0. Apply Kirchoff's voltage rule to ABCDA, we will get I1P plus I3Q minus I4S minus I2R is equal to 0. Now when the points B and D are in the same potential, the bridge is said to be balanced. As there is no potential difference between B and D, no current flows through the galvanometer, so I can write Ig is equal to 0. When you substitute Ig is equal to 0 in this equation, you will get I1 minus I3 is equal to 0, or I1 is equal to I3. Similarly, substituting Ig is equal to 0 in this equation, you will get I2 minus I4 is equal to 0, or I2 is equal to I4. So from these two equations, after applying Ig is equal to 0, you are getting I1 is equal to I3 and I2 is equal to I4. Now apply Ig is equal to 0 for this equation. When you apply this, you will get I1P plus minus I2R is equal to 0, or I1P is equal to I2R. Similarly, applying Ig is equal to 0 in this equation and substituting I1P is equal to I2R in the same equation, finally you will get I3Q is equal to I4S. Now you are getting two equations. You have obtained two equations. I1P is equal to I2R and I3Q is equal to I4S. Now divide these two equations. When you divide these two equations, you can able to find that I1 and I1 will get cancelled on the left side and I2 and I4 will get cancelled on the right side, because I1 is equal to I3 and I2 is equal to I4. Finally, you will arrive at P by Q is equal to R by S. So this equation P by Q is equal to R by S is the condition for bridge balance in Wheatstone's bridge. Only under this condition, the galvanometer shows null deflection. Suppose if we know the value of two adjacent resistances, the ratio of the other two resistances can be calculated. Among the four resistances, if any three of the resistances are known, then the value of the unknown resistance, that is the fourth resistance, can be determined using the equation P by Q is equal to R by S. And now you can able to see in this diagram, the diagram represents a galvanometer. This is the galvanometer used in a physics laboratory. What is a galvanometer? It is an instrument used for detecting and measuring even a very small electric current in a laboratory. It is extensively used for comparing the potential difference between various points of a circuit. Next, meter bridge. A meter bridge is another form of Wheatstone's bridge. A meter bridge consists of a 1 meter long manganese wire AB. So this is a 1 meter long manganese wire. This 1 meter long manganese wire is stretched on a wooden board, and this 1 meter long manganese wire, which is stretched on a wooden board, is placed between stretched along two copper strips. See in this diagram, this is one copper strip, this is another copper strip, and this is another copper strip. The three copper strips are placed on a wooden board in a meter bridge such that a gap G1 is enclosed between this copper strip and this copper strip, and the gap G2 is enclosed between this copper strip and this copper strip. The 1 meter long manganese wire is stretched between the 2 points A and B in the meter bridge. By the side of the wire, a long 1 meter scale is attached, and this is about the construction of a meter bridge. Now let us see how we are going to find the unknown resistance of a given coil of wire using the meter bridge. Now let us take Q is a known resistance which is connected across the gap G2, and B is an unknown resistance whose value is to be determined. The unknown resistance is connected across the gap G1 of a meter bridge, and between the end A and B of the meter bridge wire, a battery of EMF, a cell of EMF, a cell or a Leclanche cell of EMF E is connected in series along with the key. So this forms a closed circuit. From the end E, from the terminal E of the copper strip, a galvanometer and a high resistance and a jockey are connected in series, so that the jockey, which is nothing but a small metal wire which is made to make contact with a part of the wire. So this forms another circuit. Keeping a fixed value of Q in the known resistance, the position of the jockey on the wire is adjusted so that the galvanometer shows zero deflection. Now the length AJ represents the length L1 for balancing length, and the remaining portion JB represents the length L2, so that L2 is equal to 100 minus L1. Now this resistance P, which is an unknown resistance, forms the resistance resistance corresponds to the resistance P of the meter bridge, P of the Wheatstone's bridge, and Q corresponds to the resistance Q of the Wheatstone's bridge, and if a smaller represents the resistance per unit length of the meter bridge wire, and for the length L2, the resistance of the portion AJ becomes R into AJ, and this R into AJ corresponds to the resistance R of the Wheatstone's bridge, and the portion JB having a length L2 will have a resistance of R into JB, which corresponds to the resistance S of the Wheatstone's bridge. Now, since the jockey is adjusted to get zero deflection, we can use the equation P by Q is equal to R by S for the Wheatstone's bridge. I can write P by Q is equal to R by S. Instead of R, substitute R into AJ, and instead of S, substitute R into JB. So P by Q is equal to R into AJ by R into JB. Where R is the resistance per unit length. So P by Q is equal to AJ by JB is equal to L1 by L2, where L1 is equal to the length AJ and L2 is equal to length JB. So since Q is known and L1 and L2 are measured, we can find the value of the unknown resistance P is equal to Q into L1 by L2. The bridge wire AB is soldered or joined at the ends of the copper strips. Due to the imperfect contact at the ends, some resistance might be introduced at the contact. These resistances are called end resistance. So due to end resistance, some error may occur in the reading. This error can be eliminated if another set of readings are taken with the P and Q interchanged, and the average value of P is found out. Now, using the formula P is equal to Q into L1 by L2, we can determine the unknown resistance P. Suppose if the resistance coil P is having a radius A and if it is having a length L, then the specific resistance of the material of the wire P can be calculated using the formula rho is equal to resistance into R by A, so resistance into A by L, where if small a represents the radius of the wire, then and P is the unknown resistance. Knowing the value of unknown resistance, the specific resistance of the material of the wire P can be calculated using the formula rho is equal to P into pi A square by L. So with the help of meter bridge, we can determine the unknown resistance of a given coil of wire, and also we can determine the specific resistance of the material of the given coil of wire using the concept of Wheatstone's bridge. Next, potentiometer. Potentiometer is an apparatus used for the accurate measurement of potential differences, current and resistance. A potentiometer consists of a 10-meter long uniform wire made up of manganese or constant tin, and the 10-meter long wire is stretched in parallel rows, each row having a length of 1 meter length on a wooden board. The two free ends of A and B of the wire are brought at the same side, and it is fixed on a copper strip with the help of a binding screw. So what is the difference between a meter bridge and a potentiometer is a meter bridge consists of 1 meter long wire stretched on a wooden board, but in a potentiometer a 10-meter long manganese or constant tin wire divided into 10 segments, and it is fixed on a wooden board. And here also a jockey is provided for making contact. Let us now see what is the principle on which a potentiometer works. This diagram represents the diagram for the principle of a potentiometer. Here CD represents the 10-meter long potentiometer wire. Here battery, key. A battery and a key are connected in series to the two ends C and D of a potentiometer wire. This circuit forms the primary circuit. A cell of EMF E is connected with to the end C. The negative terminal of the cell E having an EMF E is connected to the galvanometer. The other end of the galvanometer is connected to the high resistance. The other end of the high resistance is connected to the metal jockey. So the metal jockey can be made to move on any portion of the potentiometer wire. This circuit forms the secondary circuit, and this circuit having the battery forms the primary circuit. Let us now see about the principle of a potentiometer. The jockey can make contact at any point of the potentiometer wire. If the potential difference across the end G say of the potentiometer wire is equal to the EMF of the cell E, then what happens means no current flows through the wire CD, and so the galvanometer will show zero deflection. And now the length CJ corresponds to the balancing length L. The potential difference across CJ is equal to IRL. IRL is nothing but the potential difference developed across the length L, where I is the current flowing through the wire from the battery, or the resistance per unit length of the wire. Since the condition is balanced, I can write E is equal to IRL. Here I and R are constants. So EMF of the cell is directly proportional to the balancing length. E is proportional to L. So the principle of potentiometer is the EMF of the cell is directly proportional to the balancing length. For this question, when it is asked in 3 marks, the principle of potentiometer, you have to draw this diagram definitely. Next, we can see how to compare the EMFs of two given cells using a potentiometer. This is an important experiment with the help of a potentiometer. You have heard about the two primary cells, Leclanche cell and Daniell cell. Now, in this part, we are going to compare the EMFs of the two given cells, a Leclanche cell and a Daniell cell, with the help of a potentiometer. This diagram represents the diagram for the comparison of EMF of two cells using a potentiometer. Here CD represents the wire of a potentiometer, the 10 meter wire of a potentiometer. BT represents a battery, K represents a key, RH represents the rheostat. You know that a rheostat is a device which is used for adjusting the current for varying the current in a circuit. Now in this case we are going to make two connections, so two circuits. One is a primary circuit and another is a secondary circuit. To form the primary circuit, the positive of the battery is connected to the end C of the potentiometer wire, and the negative of the battery is connected to the end key. This end K of the end of the key. The other end of the key is connected to the lower end of the rheostat. The upper end of the rheostat is connected to the end D of the potentiometer wire. Here M1, N1, M2, N2, Mn. This represents a DP/DT switch, a double pole double throw switch. Double pole double throw switch is used for making the connections alternately in a circuit. The end M of here in the double pole double throw switch, double pole key M, there are 6 terminals, M1, M, M2, N1, N and N2. The end M, the terminal M of the double pole double throw switch, that is DP/DT switch, is connected to the end C, and the opposite end N is connected to a galvanometer, high resistance, and the pencil jockey. The pencil jockey or the metal jockey is made to move over any length of the potentiometer wire. E1 represents here the Leclanche cell, and E2 represents a Daniell EMF of the Daniell cell. Connect the cell E1 having an EMF E1 between the two terminals M1 and M1 and N1 of the DP/DT switch, and connect the terminal cell having an EMF E2, that is a Daniell cell, across the two terminals M2 and N2. Now keep the rheostat at a fixed position so that a constant current I will flow through the circuit. Keep the DP/DT switch on the side E1 so that cell E1 is included in the circuit. Now adjust the position jockey so on the potentiometer wire so that at one position you will get zero deflection. Now measure the balancing length corresponding to the cell E1. E1. L1 represents the balancing length for the cell E1. Next, keeping the rheostat in the same position, you make the pencil jaw, you make the DP/DT switch to be on the side E2, so on the side of the cell E2, so that the second cell E2 is included in the circuit. Now having the cell E2 in this in this circuit, included in the circuit, you adjust the position of the metal jockey on the potentiometer wire and get at what position you are getting zero deflection. For this zero deflection position, you measure the corresponding length L2 on the potentiometer wire. So for the cell E1 included in the circuit, the balancing length is L1, and for the cell E2 included in the circuit, the balancing length is L2. By the principle of potentiometer, E1 is equal to IR-L1 and E2 is equal to IR-L2, where L1 is the balancing length for the cell E1 and L2 is the balancing length for cell E2. Divide this equation by this equation, you will get E1 by E2 is equal to L1 by L2. So knowing the measuring the value of L1 and L2, we can compare here the EMFs of the two given cells. The experiment can be repeated by adjusting the position of the rheostat so that a constant current flows through the circuit. Repeat this experiment several times and finally the average value of EMF of the two cells can be calculated. In this way, potentiometer helps us to compare the EMFs of two given cells. Thank you.